Hello everyone, myself SNEH Suman Purbia from group 316. Here is my topic human ear. First, how are you listening to the music right now? Well, you might know that your speakers are creating sound, but there is lot more going on here. You will see all your speakers are doing right now is vibrating the particles of the air close to it, and so on and so forth. So we call this as a sound wave. Start vibrating, we hear the sound, but how does something as boring as air molecules going back and forth make us experience some things like this? Well, for that we need to look at our ear carefully. I mean the entire structure of the ear. So let us look at how the different part of the ear are there. So our ear can be divided into three parts. First, the outer ear, second, the middle ear, and the inner ear. It is the part you see and touch. And the outer ear, it's the job to collect as much as sound as possible. So let's repeat the whole scenario in my notebook. First, audition. We will investigate the sense of hearing in this. This is particularly important sense for the medical physicist in many hospitals. The clinical services of the audiology is provided or supported by a medical physics personals. Let's study the physics of the sound. A sound wave is a mechanical wave that moves through the medium as particles in a medium are displaced relative to each other. It should be therefore be anticipated that the mathematical distributions of the sound will be similar with the description of the another mechanical dynamic system. The simplest possible dynamic system is the harmonic oscillator, consisting of a point mass attached to the earth by an ideal massless spring. So let's study simple harmonic oscillators. If the mass is displaced from the equilibrium position by an amount x, then the force will be developed in the spring that tries to restore the system to the equilibrium condition. This restoring force, let's say F, is acting on a mass that is proportional to the extension of the spring and act in a positive x direction when the spring is compressed. We can see this as a formula F is equal to minus kx. By the Newton's second law applied to the mass yield, the equation is comes like minus kx is equal to F is equal to ma, which is equivalent to the mx, where denotes a differentiation with respect to the time. Let's study now the anatomy and the physiology of the ear. The ear serves as a transducer that convert the mechanical energy of the incoming sound wave into a electrical energy for onwards transmission to the brain. In this context, it is similar to the microphone, which also convert the mechanical oscillations of the sound wave into electrical signals. In fact, the ear is remarkably good earphones able to accommodate sound intensities that differs by the factor of 10 to the power of 10. You can see this diagram of the ear. You can see this is the outer ear, which consists of a pinna and the external canal and the eardrum. Then we have a middle ear, which contains the bones malleus, incus and stapes, and we have a inner ear, which consists of a cochlea, vestibule, semicircular canals, and another things. So first, the primary functions of the ear. The conversion of the mechanical to the electrical energy is accomplished by the inner ear. In principle, the mechanical sound converts energy is presented to the entrance to the inner ear, and the electrical signal is transmitted onwards by the cochlear nerve. We shall find, however, that the pressure fluctuations associated with the incoming sound wave are rather small, and that our application devices is needed. If sound at our lowest threshold of intensities are to be heard, therefore the inner ear is filled with a fluid, and the fluid has a rather different impedance to that of the air through which the incoming sound wave arises. This would mean that a large proportion of the energy of an incoming sound wave would simply be reflected back from the interface, the middle ear, that serve both as a amplify the incoming sound pressure and to match the impedance of the inner and the outer ear structure. The outer ear is primarily a collecting and funneling device, although its physical characteristic do give rise to a particular efficient response to sound wave with frequencies of around 3 to 4 kilohertz. Let's study detail of the outer ear. Outer ear consists of a pinna and the ear canal, the inner boundary of which is the eardrum. The pinna, the external auricle of the human, serves a little useful purpose apart from being somewhere to hang an spectrals and miscellaneous decorative device. The ear canal, auditory canal, or external canal is roughly the shape of a tube that approximately 30 millimeter in length and 6 millimeter in diameter. The air in the tube will resonate at a particular frequencies determined by the length of a tube and by the boundary condition at the end of the tube. The ear canal is closed at one end by the eardrum and open at the another. You can see in this the picture also. Now, the eardrum, the tympanic membrane or a tympanum, forms the boundary between the outer ear and the middle ear. It vibrates in response to the incoming wave and transmits the vibration into a small bones into the middle ear. It is a thin membrane of a tissue approximately 0.1 mm thick with a cross section area of about 60 mm square. It can be damaged, ruptured, or perforated by the sound of a high intensities uh, about above 160 decibel. But in common with another tissue, it does have the capacity to heal our periods of the time. Now let's study the middle ear. The middle ear is an air-filled cavity in the temporal bones of the skull. Its outer boundary is the eardrum, and its inner boundary are the oval window and the round window at the entrance of the cochlea. The cavity of the middle ear has a air vent to the pharynx through the Eustachian tube. The purpose of this venting is to equalize the air pressure on the either side of the eardrum. The vent is not open at all the time, but it is opened by the actions such as chewing, swallowing, yelling. The main mechanical component of the middle ear are the ossicles, the small box. They each have a distinct shape from which they derives their common names. They are hammers, malleus, and the oval shape incus and the stripper shape stapes. The function of the middle ear is to amplify the pressure from the incoming sound wave and to match the impedance of the air filled ear canal and the fluid filled cochlea. You can see in this diagram also is the 2D representation of the ear. You can see the outer ear, eardrum, and we say that this component is the outer ear. Now you can see this chamber as a middle ear and this chamber as a inner ear. In a middle ear we have a hammer shape, humerus, malleus, and incus, and the stapes here. And we having in an inner ear we having a round window and a oval window. Now let's see the inner ear. The inner ear is a multi-chamber cavity in the temporal bone of the skull. It is said that it is the best protected of the organ associated with the sense. It consists of a several parts including the cochlea, the saccule, the utricle, and the semicircular canal. The function of the saccule is not known, and functions of the utricle is a utricle and the semicircular canals are associated with the sense of the position and the balance. Only cochlea has a role of the hearing process. The role of the cochlea is to convert the mechanical energy presented as a mechanical vibration at the oval window into a electrical energy that transmitted towards the onwards and through the auditory nerve. Let's understand the theory of the hearing. We know that the ear performs a mechanical sound energy that convert into electrical activity. What is the correlation between the frequencies and the intensities of the incident sound at a cochlea and the resultant nerve impulses that are transmitted to the brain? Many eminent scientists have addressed this problem, and there is still no wholly satisfied model, but depend on how we can try and divide the processing of the data between the ear itself and the brain. A comprehensive review of the current state of knowledge is represented by the Picker in 1988 that there is a little doubt that encoding the intensities information in the term of the frequency of the nerve impulse. As discussed in a previous section, it is clear evident that the single neurons fiber at higher frequencies as the intensity of the stimulant increases, the nature of encoding of the frequency informations is rather more debated. Essentially, two alternative mechanism has been proposed. In the first, collectively known as a place theories, and the frequencies is identified by the positive within the cochlea of responding nerve. In the second, known as the temporal theories, frequencies of the sound is identified from the timing of the nerve impulses. Many audiologists consider that both the mechanism are required to describe the range of human hearing adequately. Okay, this is for today. Thank you for the today's.